Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. So untuk video kali ini kita akan belajar mengenai chemical properties of alkene. We have two, preparation of alkene and reaction of alkene. So we go to the first one, preparation of alkenes. Okay, the first reaction is dehydration. So in this reaction, alcohol will undergo elimination reaction to form alkenes and water. So the reagent used in this reaction is concentrated sulfuric acid or concentrated phosphoric acid, and the condition is in the presence of heat. So in this example, you see here is the alcohol. Okay, this one is alcohol. It will undergo elimination reaction by using either concentrated sulfuric acid or concentrated phosphoric acid, and in the presence of heat, it will produce alkenes and water. So when we look at the structure of alcohol, we will see there are two types of carbon that we will study in this dehydration reaction. The first one is the alpha carbon, okay, alpha carbon, and the second one is the beta carbon. So what is alpha carbon? Why this carbon is labeled as alpha carbon? Because this carbon is connected to the functional group of alcohol, which is hydroxyl. Okay, any carbon that attached to any functional group, we call it as alpha carbon. So the carbon that attached to hydroxyl is called alpha carbon, and then any carbon that next to the alpha carbon we call as a beta carbon. So in this reaction, OH is removed from alpha carbon and hydrogen is removed from the beta carbon, and forming the second bond in between the carbon, forming the alkenes. Okay, we look at this example. If the compound contain only one type of beta carbon, so you will produce only one product. Okay, for example, in this structure, we have 2-methyl-2-propanol. Okay, 2-methyl-2-propanol. This one is the alpha carbon. When we expand the structure, this one is the alpha carbon, and then all of the three carbon adjacent to the alpha carbon we call as beta carbon. So when we classify the beta carbon, all are primary beta carbon. So in this elimination reaction, hydroxyl will remove from alpha carbon, and then we will remove another hydrogen from any carbon here. Okay, because all the carbon is same, so we will remove one hydrogen and forming double bond in between that. Okay, let's say I remove one hydrogen here and one OH here, so we will form another bond between those two carbon, okay, forming alkene. Okay, if you have more than one type of beta carbon, so you will get mixture of product. So let's say for this example, we have 1-methyl-cyclohexanol. Okay, 1-methyl-cyclohexanol. So here our alpha carbon is here, and then we have three types. We have three carbon attached to the alpha carbon. We have three beta carbon. One is primary beta carbon, another two is secondary beta carbon. So right now we have two types of beta carbon. One is primary beta carbon, another one is secondary beta carbon. So when we have two, means that we will produce only two products. Okay, so we will remove OH from the alpha carbon, and the hydrogen we will remove either from secondary carbon or from primary carbon, forming this alkene. Okay, like alkene on the left side is produced when we remove the hydrogen from alpha carbon. So when we remove hydrogen from here, you will get double bond between this carbon and this carbon. Okay, and then when we another product is here, when we remove the hydrogen from this secondary beta carbon, you will form double bond from between this carbon and then with this carbon, forming an alkene. So one of the product is the major product. So the major product for this alkene is this one. Okay, this one is the major product. Okay, why? How do we determine the major product? Okay, the major product obtained can be predicted by the Setzeff rule. Setzeff's rule states that the major product in the elimination is the most stable alkenes, which has the most highly substituted double bond. So, how do we look? Which one has highly substituted double bond? Okay, this is your double bond. Okay, when we look at the structure, at the product on the left side, the double bond is attached to 1 and 2 carbon. Okay, 1 and 2 carbon. Okay, and then the product on the right side will attach to 1, 2, 3 carbon. So which one is more highly substituted? Of course, the product on the right side, because it attached to more carbon. Okay, this one is the major product. Okay, that is Setzeff rule to determine the major product. And then we go to the reaction of alkenes. In the reaction of alkenes, alkenes are more reactive compared to alkane because alkane only has carbon-carbon single bond, while alkene has carbon-carbon double bond. So this double bond is a site of high electron density, which is what we call as nucleophilic site. Hence, they are susceptible to electron-seeking reagent, which is electrophile. Therefore, the characteristic reaction of alkene is electrophilic addition. So, in addition reaction, the weaker CC double bond is broken and two new single bond are formed. So we look here, this one is a CC double bond. So in this addition reaction, the double bond will be broken, okay, and two new single bond are formed. Okay, two new single bond are formed. One between carbon and A, reagent A, and then another one forming between carbon and B. Okay, both A and B come from our reagent, the one that we added to our carbon-carbon double bond. Okay, for the first reaction is hydrohalogenation. So this reaction will convert alkene to haloalkane. So we have alkene react with HX, our reagent, produce haloalkane. So the reagent here is HX, which is either HBr or HCl. So hydrogen and halogen are added to the adjacent carbon of carbon-carbon double bond. It will be added here. Okay, it will be added at the carbon-carbon double bond. Okay, so the addition of H and X will follow Markovnikov rule. So, Markovnikov rule states that in the addition of HX to an alkene, the hydrogen atom is added to the carbon atom of the double bond, and that has the greater number of hydrogen atoms. Means that our hydrogen will be added to carbon with more hydrogen, and our halogen will be added to carbon atom with less hydrogen. Let's look at an example. Okay, here we have an alkene, 1 propene. So when we divide the structure at the carbon-carbon double bond, you will see carbon double bond on the left side only has 1 hydrogen attached to it. This one only. This one is C. Okay, it will only has 1 hydrogen attached directly to the carbon-carbon double bond. And then, while the carbon on the right side has 2 hydrogen attached to it, means that the hydrogen of HBr will be added to the right carbon. So dia akan attach kat sini sebab yang ni lebih banyak hydrogen. And then our Br, our halogen will be added to the next carbon, okay, which has less hydrogen. Okay, how about this example? Okay, we divide the molecule at the carbon-carbon double bond. Okay, you will see here carbon of double bond on the upside. Okay, on the upside, it contain no hydrogen, does not directly attach to any hydrogen, but the carbon at below attached to 1 hydrogen. When we expand this structure, we will see the number of hydrogen attached. So this carbon attached to 1 hydrogen. So our hydrogen from HCl will bonded with carbon at the bottom. Okay, the hydrogen will be attached here, and then our chlorine will attach to the carbon above. Okay, so when we look at the mechanism how our hydrogen and halogen is attached to the carbon-carbon double bond, we have two steps. The first one is addition of hydrogen of HX to the carbon-carbon double bond. Okay, in the first step, the hydrogen will be of the hydrogen of the HX will be added to carbon-carbon double bond. Okay, since that we know that the mechanism is the reaction that will show us the movement of electrons. So in this example, the electrons, the carbon-carbon bond that has higher electron density, while the hydrogen of HBr has lower electron density. So the electron density here is high, and the electron density here is low. So the electron will move from the high electron density to the lower electron density. So means that the arrow will start from the carbon-carbon double bond to the hydrogen of HBr. Okay, and then since that we want extract hydrogen from the HBr, means that the bond between H and Br must be broken down. So the H and Br bond is broke heterolytically, and the electron of the bond is moved from the bond towards the bromine. And then following Markovnikov rules, the hydrogen is added to carbon that has more hydrogen. So hydrogen of HBr will be added to carbon on the right side, and then the carbon on the left side will leave as carbocation. Okay, carbocation plus our bromine will become Br minus because it receives electron. Okay, we go to the step 2 of addition, or which is addition of X minus to the C plus. So in step 2, we will add X minus to C plus. So for this example, we will add Br minus to the carbocation. Since that Br has more electron compared to the C plus, so our arrow will start from Br minus to carbocation, forming bond between the carbocation and the Br minus. Okay, forming our product. So that is the mechanism of hydrohalogenation reaction. Okay, we look at the another reagent of hydrohalogenation, which is HBr. Okay, dissolved in peroxide H2O2 or ROOR. H2O2 and ROOR here we call as peroxide. So when we have hydrogen bromide dissolved and in this peroxide, the addition of H and Br will follow anti-Markovnikov rules. So in the anti-Markovnikov rule, it is stated that in the addition of HX to an alkene, the hydrogen atom is added to the carbon atom of the double bond that has the less number of hydrogen atoms. So for the summary, means that the hydrogen will attach to the carbon atom with less hydrogen, and the bromine will added to the carbon atom with more hydrogen. Okay, we look at this example. Okay, we have this alkene. When we divide the alkene, so we will see the carbon on the left side only attached to one hydrogen, while carbon on the right side attached to two hydrogen. So according to anti-Markovnikov rule, the hydrogen of HBr here will added to the carbon with more hydrogen, while the bromine will be added to the carbon the hydrogen of HBr will be added to the carbon with less hydrogen, while bromine will be added to carbon that has more hydrogen. So hydrogen will be attached here, to the carbon on the left side, while bromine will be attached to the carbon on the right side. Okay, this is this anti-Markovnikov rule happen when our HBr is dissolved in peroxide. Okay, we look at the second reaction, which is hydration. In this reaction, the alkene will be converted to alcohol. So this one is alkene, react with the reagent of hydration, it will be converted to the alcohol. So the reagent used here is either H2O dissolved in H2SO4, or diluted sulfuric acid, or acidified water. Okay, so in this reaction, the hydrogen and the OH are added to the carbon of carbon-carbon double bond. So the addition of H and OH follow Markovnikov rule, which is our hydrogen will be attached to the carbon atom with more hydrogen. Our hydroxyl will attach to the carbon atom with less hydrogen. Okay, we look at this example when we divide the carbon-carbon double bond. So we see carbon on the above doesn't attach to any hydrogen, while carbon on the below will attach to the only one hydrogen. Means that hydrogen will be attached to the carbon at the below, while OH will be attached to the carbon at the above. okay, forming this alcohol. Next, we have the reaction halogenation. So this reaction will convert alkene to vicinal dihalide. Okay, this reaction will convert alkene to vicinal dihalide. So to convert alkene to vicinal dihalide, so this is what we call as vicinal dihalide. Means that our halogen is on the adjacent carbon. We have two halogen attached to the adjacent carbon. We call it as vicinal dihalides. So to form vicinal dihalide, we will use reagent halogen, either chlorine or bromine, dissolved in dichloromethane or tetrachloromethane. So both halogen atom will be added to the carbon of carbon-carbon double bond. So for this example, we have our alkene react with chlorine in dichloromethane. So both chlorine atom will be added to the both carbon at the carbon-carbon double bond. So forming vicinal dihalides. So we have another one, halogenation, which is converted alkene to halohydrine. So forming forming a halohydrine. So to form a halohydrine, which is here, this one is halohydrine. So the reagent used is halogen dissolved in water. So right now, the atom that will be added to carbon-carbon double bond is halogen and hydroxyl. So halogen and hydroxyl are added to the carbon of carbon-carbon double bond. So the addition of halogen and hydroxyl are as follows. So our halogen will be added to the carbon atom with more hydrogen, while our hydroxyl will be added to carbon atom with less hydrogen. So look at this example. When we divide our alkenes, our carbon-carbon double bond, we will see that carbon at the above doesn't attach to any hydrogen. Okay, this carbon doesn't attach to any hydrogen, while carbon at below attached to only one hydrogen. Means that react with bromine aqueous, which is bromine that is dissolved in water. So bromine aqueous. So in this reaction, our bromine will be added to the carbon at the bottom. Okay, and then our hydroxyl will be added at the carbon at the above. Okay, so forming a halohydrine. We look at the last reaction, which is hydrogenation. So this reaction will convert alkene to alkane. So this is an alkane. So the reagent used here is hydrogen in the presence of platinum or palladium, which is act as catalyst. So both hydrogen atoms are added to the adjacent carbon of carbon-carbon double bond. So we look at this example. We have alkene react with hydrogen in the presence of platinum. So both hydrogen will be added to this carbon, forming an alkene. So that's all for this video. I hope this video will can help you to answer all of my question. So selamat mencuba. Assalamualaikum warahmatullahi wabarakatuh.